Alrighty. Hi everyone and welcome to the database bits of this week. This week was basically divided into two parts. During the live classes, we discussed how do you horizontally and vertically scale an application. We understood about something called capacity estimation. We understood auto scaling groups in AWS. And we tried to build a few applications that scale up and down based on load or on other metrics. What we had to skip out on was indexing, normalization, and sharding. The ticks here mean things that I thought we'd be able to cover in the live class. Unfortunately, we weren't able to cover indexing. So in this video, we'll cover indexing, normalization, and sharding, the three important system design concepts when it comes to database. It's not just system design. You also need them. You also implement them, but you don't need them for a long time. Unless you have scale, and by scale, I mean maybe 1 million users, unless you have a certain database that's growing a lot, unless you have a lot of customers whose data doesn't depend on each other. These don't come into the picture. At some point when you're scaling, you have a fire one day randomly because of, your queries are really slow, or, there is a overall high level discussion. We are growing our system in this specific way. For example, a small example here is, let's say you're trying to build something like, Udemy, where if you open Udemy, there's a lot of users, and a lot of times their data doesn't need to be related. For example, by users I mean educators. If there are 10 different courses, all the data that's for this course is not related to any good data that's for this course is not related to any data for this course. So you might be able to shard. Is sharding a good idea? What are the queries that are running? Are there specific queries that are extremely slow? Why are they slow? And is there a way to make them faster by either query optimization or by adding indexing? These are the things that we'll try to discuss today. It'll be highly theoretical, by which I mean, not a lot of code writing / commands. We might be doing some SQL here, but yeah, normalization, pretty much a bunch of, theoretical discussions, same for sharding. Without any further ado, let's get right into it. These are the things that we had already discussed. The thing that we're diving into next is how do you create indexes in Postgres? Even before that, what are indexes? There a slide before that? No, there isn't. There probably should be a slide explaining what indexes are. But let's kick things off. What does it say? It says indexing in Postgres. We have created Postgres tables many times now. Let's see how / if indexing helps us speed our queries. Harkirat, indexing, this is a new buzzword you've never introduced. Yes. Let me introduce that first. Before that, let me maybe share a bit. How do queries run when let's say there's a users table and you send a query called select stars from users. So select star from users. If this query goes to a specific database, what happens? There is a table in that database which has a bunch of rows. And right now this query it's a little too, long of a query. So let's make it slightly more constrained. Select star from users where user underscore ID equal to 1. So this query should ideally just return you a single record amongst these, let's say, 1 million records. What happens when you send out this search? There is a linear search that happens, which basically means you start from the top and start to look for any row where this constraint is met. If it is ever met, you return it back to whoever asked for the query. A lot of times Postgres does some optimizations. It might do this, okay, this is the query that's being asked. So let me spawn 2 threads. Let me make sure I still do a full scan of the database, but I do it, on 2 different cores of the machine so that, we're able to speed up the process by 2 times, which means this specific row will look for for a record like this in the first half of the database. And this specific core / worker will look for a record in the second half. So SQL already, or Postgres in this case, already does a bunch of these optimizations. The question is, what can you do as a developer? If you know that queries are being slow, how can you make these queries faster with data that you're providing Postgres with? Postgres already does a bunch of optimizations. What can you do on top of it to make your queries faster? Indexing is one such thing. Before we get into indexing, let's maybe try to see how long does it take for a query to run. Let's try to create a dummy database. Let's push a bunch of data inside and let's try to run some queries. See how long does it take for a query to run. Do multiple workers get spawned from time to time, or is there a single worker that's getting spawned? So to kick things off, start a Postgres table locally, which is this step right here. We have done this many times. you should start it using Docker. You can also start it otherwise, but Docker is the easiest way to start a Postgres table locally. So let me open a terminal on the right. Let me open the slides on the left, and let me before I run the first command, let me just see if I have Docker running locally, and it seems like I don't. So let me start Docker locally. There we go. Now let me run the command docker ps, and I have no containers running locally right now. So what is the command that I can run? Docker run with the port mapping 5432:5432-e, an environment variable, which in our case is Postgres_password equal to my secret pass. You can send whatever you want. Doesn't matter, whatever you want to, have the password of your Postgres database, followed by -d, which means run it in the background, and then Postgres. If I run this command, it'll start a Docker container. It happened very quickly for me because I already have the Postgres image locally. For you, it might take a longer time. If you don't understand any of this, you should go back to the Docker classes. Docker ps shows me I have a single container currently running on my machine, and this is the ID of that container. What have I done in this step? I have just started a Postgres database locally, so I can create tables, put some dummy data inside, query the data, and figure out how long does it take for a query to run. Next step is running some bash commands on this specific container. The thing is, I don't know if you guys remember, we discussed something called PSQL a while back, which lets you run commands like these on a database. You can also use Node.js if this is the database that we have just created, and now we have to run a few queries on it. We have to tell it, hey, create a new table, or select star from something. You can do this from multiple clients. There is no single way for you to send queries to a Postgres database, but one of the ways is something called PSQL, which is a command line interface, a CLI that lets you send SQL commands to a database. How can you start PSQL locally? You can either install PSQL just like I have it. If I run PSQL, it says error connecting to socket because I haven't given it the credentials of my database. But you most probably might not have PSQL locally. So what you can do is you can go inside the container by running this command docker exec -it, the container ID /bin/bash. If you remember from the Docker classes, this specific command lets you run bash commands on the Docker container. And thankfully, whenever you start a Postgres Docker container, it also has PSQL installed inside the container, so that you don't have to install PSQL on your Mac machine. So even if you don't have PSQL, what can you do? You can go inside your Docker container by running this command docker exec interactively the container ID followed by /bin/bash. The container ID will be different for you and different for me. What is it for me? It is this thing right here, 0578. So let me copy it, and then let me run the command docker exec -it container ID /bin/bash. If I run this command, as you can see, this prefix changed from this tilde to this thing right here, which means I can now run commands inside my Docker container. Making sure the mic was right. Thankfully it was. If I press ls here, it shows me all the contents inside my container. If I type PSQL here, it says connection failed. The command to run is PSQL-u Postgres. If you run this command, then you'll be able to reach the PSQL shell through which you can send queries, this is your CLI. PSQL is now your command line interface, and you can send SQL queries to the database you have just started. So I have a database running, and now I can send SQL queries to it. What is the first one to send? Let's create some dummy users, some dummy tables, in which we will eventually put some dummy data as well. But what are the tables? There's a users table, very standard in most applications. You have users who sign up, and hence you can create a users table. Let me copy this and paste it here. As you can see, it says create table. If I press the command /dt semicolon, it will show me I have a single table right now called users. Can I create another one? Yes. Let me copy this and create another table called posts. So if I now look at it, I have two tables, posts and users. Now let's put some dummy data inside. Let's put a bunch of users, put a bunch of posts. Why? Because we have to make sure we're able to run a bunch of queries and figure out how long did it take for a query to run. If we have no data there, then we won't be able to learn much when it comes to indexing or sharding. Hence, we need to put some dummy data. This is a long command that sort of, iterates over a bunch of users. Maybe before that, I hope this schema is clear. Every user has user ID, email, password, and name. So it has 4 fields. User ID is the primary key. It goes up by 1, so it's serial in nature. Email, which is a varchar 255, which basically means variable character with a maximum length of 255. It is unique and it is not null. Every user needs to have at least an email, password, and then finally name. Similarly, there's a posts table. So this is a app similar to the Medium app we have discussed many times by now. You have a posts table where there is a post ID, user ID, title, description, and image, and it has a foreign key, user ID, which means this thing references the table here. It also has a foreign key constraint. All things we've already discussed when we discussed Postgres. Insert some dummy data in is something new. Frankly, I did not know how to do this. I also Googled and figured out. So you can always run a for loop. So for I in 1 to 5, insert users. So we're inserting 5 users in our database. Let me make this full screen. We're inserting 5 users in our database. And for every iteration, for every user, we run another loop to put in 500,000 records in the posts table. So every user has 500,000 posts. That is the double for loop that we're running. Insert a user and insert 500,000 posts for that specific user. If I run this command, it'll pretty much seed my data with my table with some dummy data. If I take this over here, paste it here, as you can see, it's taking a long time because it's a lot of records to put. But once this does succeed, it'll put 5 users, and for every user, it'll put 500,000 posts in the posts table. Pretty random data in there. We'll explore the data very soon. But even if you don't understand the script, is fine. You rarely, if at all, ever use it. You should understand what it does though, which is seed your data with a lot of your table with a lot of data. If I now run the command select star from users, you will see I have 5 users: user 1, user 2, user 3, user 4, user 5. And if I run select star from posts, you will see it takes a long time. So let's put, oh god, I selected everything in a very big table. So yeah, this will just, there we go, interrupted, which is good. Let's do a select star from posts limit 5, which means just give me the top 5 posts, don't give me everything. And that's slightly faster than, querying the whole table because it has 2.5 million records now. Running a query to get all the posts of a user and then log what time it took. This is something new. This explain analyze followed by select star from posts where user ID equal to 1 limit 5 is something new. I already have a query that says select star from post limit 5, but I don't know how long it took for the query to run. I don't have any stats around it. And thankfully in Postgres, you can type explain analyze, and as the name suggests, it lets you analyze how long did this query took to run. And what does it say? It says the execution time was 0.021 milliseconds. So extremely low, as you can see. And the reason for that is, this isn't a lot of data to query through right now. We're only getting back 5 records. If you look at the count that I have in this table though, from posts, it'll probably be 2.5 million. And if you look at the explain analyze again, it says I had to scan through 2.5 million rows to be able to reach this specific answer, which means there was a sequential scan that happened on posts. We haven't done any optimization yet. This is a sequential scan, which basically means what? It means we went through the table from top to bottom. We did not even have any workers because there should be a log here that says, 2 workers were spun out. So pretty much means there was a linear search done on a single core. And the execution time is, 0.028 milliseconds, which is not too bad. We should probably put in some more data, if I'm being honest, because this isn't a lot of, this isn't too long of a query for us to put an index on. So let's do that, if I'm being honest. Let's increase. Actually, the query is wrong. That's probably why the query is so fast. I'm just getting the top 5 records. I'm not getting the top 5 records for a single user. So what happens when I run this query is it tries to go through the table and 1, 2, 3, 4, 5 finds the 5 rows and returns it. If I change the query to be this though, give me all the users where user underscore ID is 2. Then as you can see, the execution time blew up. It is 47 milliseconds now. Might not seem like a lot, but compare it to what we had before. Before it said 0.021 milliseconds. Now it says 47 milliseconds. That's like 1,000 times more or something like that. So now comes the tricky bit. When you start to search through a table, I don't need the first 5 rows. I need the rows that follow these constraints where user ID equal to 2. Is when SQL becomes slow, as it should. It might go through from the top. It cannot find any user for the first 500,000 rows, then goes again, cannot find any user, and then finally finds it. So it had to go through so many records to finally reach what you want. Versus when we just asked it, give me 5 records, it just took the top 5 records and returned it to you. If I run this again, as you can see, it still says sequential scan on posts, which means we're still going through everything from top to bottom. Earlier, we were able to find 5 very quickly. Now it took us a long time. The time is slowly going down 0.0130 milliseconds because we're repeating the query. But if I make this something else, user ID equal to 5, it still says 88 milliseconds. So the time is still a lot. How do you make this faster? This is the crux of indexing. Most of the times when you're querying a table, you're querying it on some constraints. Give me all the posts for some user. You're also limiting your records. Rarely do you ask the database, give me 1,000,000 records. Most of the times you will ask, can I get 5 records or can I get 10 max? And you'll have some sort of what's called pagination on your website. Pagination means there are pages. So when a person comes to your website, they will see a bunch of data here, and then they'll see a previous button here, previous page, and then a next button here called the next page. So at a time, we expect users to only ask for 10 records. So let's say there are 10 records here. So the query sort of looks something like this, where we limit the amount of things we want from the database. We don't want everything for a user. Question is, how can you make this search faster? How can you ensure when you're asking the database for some data and you have certain constraints, how can you tell the database, I will be having these constraints, these queries, please somehow make it faster. Cache the data, put the data somewhere else, maintain some data structure. But I am upfront telling you, I'm going to send you queries that look like this, where I will ask you, give me the users where user ID is something. Please make sure you optimize this query and return me this in much less than whatever. It's again less now, but let me change this to 4 or 3. Then you'll see it's 82 milliseconds again. How can I make this lesser? By telling the database upfront something. What is this something I can tell the database? And the answer is indexes. Focus on the execution time. It was really high. Let's add an index to a user ID. But before we add an index, we need to understand what exactly is an index and how does it make the queries faster. Let's understand that next. All right. Maybe before we proceed to understand how indexing works, let's try to run this query. Let's see, does it improve the time it takes for the query to run? This isn't too hard of a line to understand. It says create index. This is the name of my index. I've called it idx underscore user underscore ID on the table posts with the user ID being the field that we index on. Where does this user ID come from? It comes from the fact that when we're querying, our constraint is on user ID. If we would have constraint on other things, then this specific thing would have been something else. But what is this query trying to tell the database? It's trying to tell the database, okay, hey, I will query you a lot based on a constraint on user ID. So please index yourself on this constraint. Now, what does indexing mean? We'll come to very soon. But before that, let's try to first, what was the time that it took for a query to run? Let me change this to user ID equal to 2. I've already done that. So it's sort of cached. Let's make it 1. 90 milliseconds. What's the time? 90 milliseconds. Let me exit out of this and go back in so that, it still remains like a lot of time. Now the execution time is really low for all user, let's put a random user ID. There you go. 64 milliseconds. Returned no rows because there is no user with ID 9, but that's fine. Let me try it with user ID 11, same thing, 65 milliseconds. Let me try with user ID 12, same thing. Execution time 63 milliseconds. Very expensive operation, but let's try to run this line of code. It says create index, which means the index has been created. Now let's try the same thing again. Let's try user ID equal to 13, and let's see how long does it take for this query to run. And as you can see, it says 0.059 milliseconds. That seems like a stark difference. Is there some caching happening? Let's change the user ID. No, without any caching, irrespective of what query you're sending, the time is extremely low. What happened? What did this one line of code do to take the execution time for a query in a very big database down from 63 milliseconds to just 0.045 milliseconds? That's a very big difference, like 1,000 times faster. Why? And the answer is indexing. Let's see what that means. When you create an index on a field, for example, we have created an index on the posts table on the field user ID. A new data structure, usually a B tree, but you can change this data structure, is created that stores the mapping from the index column to the location of the record in the original table. Let's understand what that means. What is the index column? What is a B plus tree? What is the location of the record in the original table? What is the current problem in our current approach? If we don't have an index, what is the problem? The problem is we do a full scan, which means if I ask the database for something, it starts from the top, goes through all the 2.5 million records that are there, and then eventually takes 65 milliseconds to figure out, okay, is there any data that matches these constraints? But what if I told the database, okay, hey, all the users with ID 5 are actually present here, so please start your search from here, or please do whatever you're trying to do on here, 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 and here. What if I somehow have cached this someplace else in the index? That's sort of how indexes work. Whenever you run this query, which I ran over here a while back, the query was create index IDX user ID on posts user ID. Something new was created. A data, what is a data structure? Something that stores data, right? That's what a data structure is. An array is a data structure, and objects are data structures, and similarly, another data structure is created. What is the data structure changes based on your requirements usually, but that data structure does something special. Let's see what that is. Let's look at this diagram here. This is the full search. You have 0 indexes, but this is what happens when you create an index. A new data structure is created and it has your index column. What did we index on? We indexed on the user ID. So it stores your index column on one side and the location of this record on the other side. Harkirat, what does location mean? Assume location is, the actual memory address, or, actual storage mein it's present on this byte. Let's say, all this data is present in a file called, a.txt. Assume, okay, all the rows are present in such a file called a.txt, user 1, user 2, user 3, user 4, so on and so forth. Or, post 1 in this case, actually. Post 1 has title Harkirat, has description, whatever. And then post 2 has another title, has another description, post 3, so on and so forth. Let's say these are all stored like this in a file. That's not how Postgres stores data. Postgres stores data a different way. But let's assume it's just present in a file like this. Then this mapping stores here user ID 1's post is present over here. User ID 1's post is present over here, so on and so forth. All the posts of user ID. Let's say user ID had, user ID 1 had 5 posts. Then there would be 5 rows here for ID 1, ID 1, ID 1, ID 1, ID 1, and the location of those posts. Maybe a better example to give is, let me copy this specific thing right here on the left, and let me add a new row here called 6 with user ID is again 1. The user ID 1 made another post, user 1 post. Let's the description is also hello. So I've added a 6th row here. Then what would the index look like? The index would look something like this. User underscore ID, and then location. What is the location of the post for user ID 1? It is, it will be something over here. What that thing is depends on how Postgres stores data. As I said, it could just be, the line number here. Post 1 is present on line number 1, but actually it's something else. It's pages and offsets, which is how Postgres stores data, but we're not going there just yet, or maybe at all during this class. Second, sixth, actually it will not be site, it will be one, and then I'll share what this 6 is. So just keep it random over here. Let's keep it something random on the right, and then 2, which has something, and then 3, which has something, 4, which has something, and 5, which has something. This says, this is an index on the posts table with the user underscore ID as the field we're indexing on. And we have a sorted list. I repeat, this list is sorted 1, 1, 2, 3, 4, 5. Even though user ID 1 had the first post here and the second post at the end, as you can see, the thing on the right, first one, this thing right here points to this record, the first one. And the second one, what do you think it points to? It points to the last record right here. And then 2, of course, points here, 3 points here, 4 points here, 5 points here. My point is, this thing is sorted. The whole point of this is, I will store everything sorted based on the constraints of the index. So if user ID is what we are asking a lot of questions on, I have this sorted list of user IDs. User ID 1 has 1 posts at this location, has 1 post on this location. User ID 2 has 1 post on this location. User ID 3 has 1 post on this location. If the user 3 adds another post, I will add it over here. I will not add it to the end of the index. I will add it over here. This way, I have a sorted list of the person with user ID 1. These are your location of posts. Person with user ID 2. These are your location of posts. Person with user ID 3. This is your location of the post, so on and so forth. Why is this good? This is good because now if I ask you, hey, give me all the posts of user with ID 3, what can you do? You can binary search here first. You will not do a full scan. You will not start from the top. Is this the row? No. Is this the row? No. Is this the row? Yes. So you're trying to do a full scan. What if I give you the ID as 5? Then you have to go from the top and then eventually reach the last row, right? Or second last row. So that's order of n versus now if I give you, give me the posts of a user with ID 5, what will you do? You will be like, okay, ID is 5. Let me go to the index. Let me go to the middle of the index. Is 5 greater than 2? Yes, it is. Then it means it lies in this half. Then you'll be like, is 5 greater than 4? Yes, it is. Then you'll be like, it'll lie in this half and you'll finally reach the right row. 5 exists over here. And the pointer to this points to this location right here. So in order of log of n, if you've done binary search, this is straightforward. But if you haven't, you first have to understand what binary search is. But that is what we're taking a benefit of over here. We're saying whenever the user says select star from users where ID is equal to 5, what does the user say? Select star from users where ID equal to 5. When the user sends you this query, rather than going to the table directly, you first go to the index. You binary search on the index. You find, okay, what is the first record for ID 5? And when you reach there is when you, in order 1, can directly reach the pointer to the row. You don't have to go from the top and, do a linear search. That is one way to create an index. This isn't the popular one. The thing on the right usually isn't a list that's sorted. It's a B tree, which out of scope for this video, but not very common data structure, very late advanced data structure concept called B tree, which pretty much tries to do the same thing. It tries to, in order of log of n, tries to return you a row, basically a row containing, a pointer to another record in the original table. If this is the original table you're trying to search, the goal of the index is in order of log n or in some order that's less than order of n, try to return me the address of the row so that I can directly reach the row rather than doing a full search on the database. That is how the query became faster. Now, if you did not understand this, it's mostly fine. I never understood this, and I just did it in college once and then forgot about it. All I knew was indexes make your query faster. There are some very advanced use cases where you have to understand what are indexes and optimize them. But most 99.9% of the times you have to create an index, forget about it. When you're creating the application, when you're writing the code of your application, you just have to make sure you find out these constraints. You find out all the queries that we're doing, here, these are the constraints we are calling again and again. So I need to create an index by running this command. What you don't have to worry about is, this is how under the hood the queries are getting run. And there is a new data structure that's been created that's making this query faster for a long time. Sometimes, as I said, you have to understand this and choose, a different data structure based on the current use case. But most of the times B-tree just works and, is fairly, will cover most of the use cases that you'll encounter in a full stack application. Alrighty, let's see what did we do. Let's do a quick recap. We said we're introducing indexing in Postgres. So we started a Postgres database locally. We connected to it and we opened a PSQL shell there. We created 2 tables inside and then we ran a query to put a lot of data in there, a lot of users and a lot of posts. Then we tried to run a query to get all the posts of a user and log the time it took for that. Given a user, there are 2.5 million records, which is why this was taking a really long time. The execution time was almost 63 milliseconds, my bad. Then we created an index and ran the same query and the execution time went down to 0.01 milliseconds, something like that. It became significantly faster. How? Because we avoided a full search, a full scan, and we created an index which did something like this along with your original table, created another data structure, which in this case, created another database, created another database, but created another table, this isn't a table. So don't say this out loud. Okay, created another table. Assume it created another table that you can binary search on that is sorted already from top to bottom. And whenever a query comes to you, select star from posts where user ID equal to 5, you binary search on this column and eventually reach this section right here. The question you should have at this point is, Harkirat, how is insertion log of n? If I say I'm going to insert another post here for user ID 2, how will you put it here in log of n? If you try to put it here, all the rows will move behind. So insertion might be order of n. And the answer is yes. That is why you use a B tree where both insertion and query are log of n, which tells you what? It tells you, okay, if you do add an index, there is an overhead. If you do add an index, you are not just inserting your row. You are not just doing this insert. You're also inserting something extra here. So your write will become slower. I repeat, your write will become slower slightly. You don't worry about that. That's not a problem because number one, most applications are read heavy. Number two, write is becoming heavy by little bit. It took 0.01 milliseconds here. It'll take extra 0.01 milliseconds. It's fine. Read becomes extremely slow if you don't have an index, which is why there is an overhead. You have to put things 2 places whenever an insertion happens now when you have an index. But that is fine because the reads are what you optimize for, because most applications are read heavy. If you go to app.100xdevs.com, most people are asking for the content. Whenever you log in, the content that you see, most people are asking, give me the content. And rarely does a new video get added, right? Twice every week, thrice every week, which is why you optimize for reads and not for writes. And even if the writes are a little bit more expensive, it is fine as long as the reads become significantly faster. The data pointer in case of Postgres is something called the page and the offset at which this record can be found. So, I've just put random numbers here on the right locations, but when you actually store this in Postgres, the thing that's stored here in case of Postgres is something called the page and the offset, for which you have to understand how actually Postgres stores data under the hood, which feel free to, but not really needed at all or for a really long time. Think of an index as the appendix of a book and the location as the page plus offset of where this data can be found. I don't know how many of you have seen appendixes of book, or if you read books. I don't, so I had to Google this. But appendix of a book basically looks something like this. If you've seen it, okay, this is not a good appendix. No. It's not exactly contents, but yeah, take feel free to look at this. Okay, thanks can be found on page 13, and hello can be found on page 15, and this thing can be found on page this. So you're reverse searching. Okay, given I have this word, where all can I find it? That's what we're doing here, right? Okay, given the post ID is 5, where all can I find it? Directly tell me, please. I don't want to search. If I give you a book without an appendix, you will have to go through the book completely from the top. You will have to do a full scan on the book to find hello in the book. But if I give you an index where I clearly tell you कि hello is present here, then you can go to the index, quickly look at the word hello, find the pointer कि where is it present, and directly go to that page. That is what indexes do under the hood. So very, if you think of it from first principles, very easy to understand what is the goal of an appendix, and similar is the goal of a index in Postgres. With that, let's move to slightly extra, something called complex indexes, which shouldn't be too difficult to understand if you understood indexes. The thing is, not every time your queries would be, as simple. Okay, select star from post where user ID equal to something. A lot of times they'll look like this. Select star from posts where title equal to some title and description, let's say, if that was a field here, equal to something. It'll have two things to search on together, not one thing. I need to put single quotes everywhere. Something like this. This suffers from the same problem. If you try to do this, where title equal to something and description equal to something, and limit 100, explain, analyze, you will see it took 83 milliseconds for the query to run. Even though we have an index on the user ID, we're not searching based on user ID anymore. We are not searching based on user ID. We are searching based on title and description, which means what? It means the index that we had won't work anymore. We have to create a fresh index. The more the type of queries you have, by type I mean, this one looks for title and description, another one looked for user ID. The more these types of queries you have, the more type of indexes you have to create. Each query will have its own index based on the constraints on which you're searching. So for this one, how can I make this specific query faster? And the answer is simple. Rather than creating an index on just user ID, I'm saying create index. I have given the index a name on posts on two fields. I'm creating a compound index, a complex index. What's the right word? Complex. A complex index. I'm saying here both description and title are what are needed in this specific query. So create an index on both of them. Takes some time. We will wait. There we go. And now if I run the same query and let's say change, description to something random, title to something random, now it took 0.06 milliseconds. So always look at your query constraints and then create an index for it. Under the hood, same thing is happening. Rather than having user ID here, we are now be having, title, and then the second thing will be description and then location. And then, for all the titles and descriptions that exist here, for example, hi there and hello, we'll have the location. Okay, so the location of hi there, hello, title, description is this. And then the location of whatever, user one post, and then whatever the description is over here, hello is over here. Again, it will be sorted, which means you'll first have 5 rows of hi there, hello, 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 and then 1 row of user one post and hello. It will be sorted. The sorting isn't too difficult, right? Even if you have 2 fields, it still means you sort based on, let's say, the combined word. Okay, hi there, hello is the first word. User one post hello is the second word. Sort them based on, alphabetical sorting. So hi there, H comes before U, and hence this is the first row. And you will have 5 such rows because we have 5 such columns here with the same title and description. And then the last row would be this. So you will have, first you'll have 5 such rows, and then the last row will be this. This is how the index would be created on title description. Earlier we saw the index on user ID. How will this point? This will point to this row, and this will point to this row. It will pretty much be linear because in this case we got lucky, and the data on the left is also sorted already. But you cannot assume that this last row might have been inserted, way up here. So the thing on the right is sorted. Thing on the left doesn't necessarily have to be sorted. What did we learn? We can also create complex indexes. We have to create complex indexes if we have complex queries like these, and make sure these queries where multiple constraints are present also become faster. That is what a complex index is. Lastly, we have one more thing to discuss in indexing, which is, Harkiyat, you shared how to do this in Postgres. Can you share how to do this in Prisma? And the answer is fairly straightforward. Prisma, of course, provides you a construct to do this. You have your schema.prisma file where you've been putting your models until now, is where you can put a line like this. Okay, hey, I want to create an index on the field user ID so that every post of the user is indexed on user ID. And that is all you have to do. This will, under the hood, create that SQL query. If I sort of take this and put this in a Prisma.schema file locally, the final SQL that you see, you will see an create index query over there, because Prisma will create that query under the hood. Let's look at a few projects or just daily code here, where I think a few places we should have indexes, but we don't. For example, this is a model called submissions. If you don't know, we're adding, lead code like problems here to projects.100xapps.com. And whenever you have such problems, you see the user submissions. This is that model. It stores the user's submissions, and we query the users from time to time. Hey, what were my last 5 submissions on this problem statement? Just like lead code, right? If I go to leadcode.com, and go to open a problem statement, I will see all of my submissions here on the left for a specific problem. Let's see if I'm logged in already. I am. So if I go to problems, if I open a specific problem, there's a submissions section here, which shows me all the submissions I made. Wow, I solved this in 2019. This query we will also need. And what do you think the constraints on the query should be for the index? What is this query? It looks something like this, right? Select star from submissions where user underscore ID equal to something and problem underscore ID equal to something, where the problem ID here is compare version numbers and user ID is my user ID. So this select star from submissions where user ID equal to something and problem ID equal to something. What do you think the index should be that we don't have right now on daily code, but we should add? What should be the index that we add to this submissions model? The answer is we should do an index on user ID and the problem statement ID. We should have an index on problem statement ID and user ID, because we will have a query that will ask the database for this. We don't have it right now, and that is fine. You see this problem way down the line when you have a lot of users where they are either spamming your database and you have to have a lot of spam data in your database, which is when you see a billion rows, or if you have a real company that has scaled to so many users. For example, LeetCode is a good example. They will have probably millions of users, each submitting thousands of submissions. So that's like a billion records right there. They do need an index on this query. We don't right now, but doesn't mean you don't over prepare from the beginning and add an index here. So if there is one thing you want to try adding an index here. If you really want to see if, this is pretty straightforward, right? So don't add it. Don't create that PR. We will eventually when we need to. But try to maybe put some dummy data here. See in the UI, is this query slow when I open the whatever, when you set this project up and you open a problem statement there and you try to do a submission and then fill this submissions table with a lot of dummy data, and then try to look at the submissions and see how this query is really slow on the front end, and then add an index and then see how quickly it comes back from the database. So decent exercise to do, or like take it as an official assignment at this point. To number 1, what do you have to do? Set up daily code locally. Number 2, add a problem statement in there, lead code like. Number 3, make some submissions. Number 4, put some dummy data in there. And then number 5, try to query from front end, see it is so slow. And then lastly, try to query, add an index, and then try to query from FE again and see the query time go down. Cool. This is an assignment that you should try out locally. This will teach you not just SQL, but the important things. What we're learning is like writing an index, even if you don't understand it, someone will say create an index whenever you join a company, or now you understand it, you know how and when to create an index on, that day when the query becomes really slow. That's usually how indexes are shoved into a company. Rarely do you, from the beginning over prepare on indexes. It's a good idea to do, but people are moving fast, so you don't really look at it. You create your schema Prisma, your Prisma schema, and you just forget about it. So that's the easy bit. Anyone can put a line of code here. The difficult bit is doing all of this, simulating it locally, because you can't just put an index here and create a pull request. What if it doesn't do what it says it does? How do you know it has actually fixed the issue? This is the difficult bit. It is a one-line issue. It should take 2 minutes, but it takes an hour because this. You learn a lot because of this. So please set it up locally, do all of these steps, and then go from there. With that, indexes are done. Next up, in the next video, we'll understand normalization. If you have gone through a DBMS class, you've probably learned more there than here. If you haven't gone through a DBMS class, then it should teach you a lot of things. Although this is highly first principles, which means, even if you don't understand normalization, you should be able to understand, this is what it does. And, this is why you need to understand it. And this is how you create tables for an SQL database. Let's understand normalization next.